MS Ramaiah University of Applied Sciences.
Hi students, let us discuss unconfined compression test. The aim of the experiment is to determine the unconfined compressive strength of the given clayey soil as per IS 2720 Part 10 1991. Shear strength is the major engineering property of soils. Unconfined compressive strength of a soil sample is defined as the load per unit area of an unconfined cylindrical soil specimen. Will fail in axial compression test. This test is undrained since the rate of applying load is very fast. In this test, pore water pressure does not dissipate. This is the simplest and quickest method for determining cohesion and shear strength of cohesive soils. Unconfined compressive strength helps to check the short-term stability of foundations and slopes where rate of loading is fast but drainage is slow. If the axial compressive force per unit area has not reached a maximum at 20% axial strain, unconfined compressive strength is taken as the value obtained at 20% axial strain. Failure plane is not predetermined and hence the failure takes place along the weakest plane. Experimental setup. Compression device, that is loading frame. Proving ring of suitable capacity. End plates which are frictionless, that is greased plates. Deformation dial gauge. Mold of internal diameter 38 mm and length 76 mm. Sample extractor, weighing balance. Experimental procedure. Soil sample for the test should have a minimum diameter of 38 mm. Largest particle contained within the test specimen shall be smaller than 1/8 of the specimen diameter. Mix the sample carefully to avoid any entrapped air and to obtain uniform density. For the desired water content W and the dry density, calculate the weight of the dry soil Ws required for preparing the specimen. Add the required quantity of water Ww to the specimen as Ww equal to Ws into W by 100. Mix the soil thoroughly with water. Place the wet soil in a tight, thick polythene bag in a humidity chamber. After 24 hours, take the soil from the humidity chamber and place the soil in a constant volume mold. Coat the inside of the split mold with a thin layer of grease or oil to prevent adhesion of the soil. Compact the specimen in compaction mold in 3 layers using standard rammers. Eject the sample from the mold using a sample ejector. Measure the height and diameter of the soil sample. Weigh the soil sample. Place the specimen on the bottom plate of the compression machine. Raise the bottom plate of the machine and make the specimen contact with the upper plate. Adjust the proving ring dial gauge and deformation dial gauge to 0. Apply the load to produce axial strain at a rate of 0.5 to 2% per minute. Record the readings of the proving ring dial gauge at suitable intervals of deformation dial gauge reading. Up to 6% axial strain, readings may be taken at an interval of 0.5 mm of the deformation dial gauge reading. After 6% axial strain, the interval may be increased to 1 mm. Beyond 12% axial strain, interval may be increased further. Apply load until failure surfaces have developed on the specimen or until an axial strain of 20% has reached. Take representative samples from the failure zone of the specimen for water content determination. Data collection and tabulation. Weight of the sample, volume of the sample, bulk density of the sample, diameter of the sample, height of the sample L, area of the sample A0, deformation rate, least count of deformation dial gauge, proving ring constant are noted. Calculations computations. Deformation delta L equal to number of divisions of dial gauge into least count. Axial strain epsilon equal to delta L by L. Corrected area A0 equal to A0 by 1 minus epsilon. Applied load F equal to number of divisions of proving ring into proving ring constant. Compressive stress Q equal to F by A0 are calculated. The stress-strain curve obtained is as shown in the figure. The maximum value of stress from this plot gives the unconfined compressive strength of the soil sample. If no maximum is observed, stress at 20% strain gives the unconfined compressive strength. Results. Unconfined compressive strength in terms of kilopascals is presented.
Dear students, today we are going to perform unconfined compression test. This test is being conducted on clays which can stand on its own without any lateral confinement. The apparatus required for this test can be divided into two. One set for sample preparation and then for testing. Now for sample preparation, we require a weighing balance. The weighing balance is used to accurately measure the soil sample. A mold which is used to prepare the soil sample. The size of the mold is of 38 mm diameter and 76 mm height. A measuring scale can be used to measure the dimensions of this mold. The measuring scale is used to measure the dimensions of the mold. Oil can, the inside surface of the mold has to be greased thoroughly. So this oil can is used to grease the mold. Stopwatch is used to measure the time while taking the readings. The tray and the trowel is used to collect the soil sample. Now let us start the experiment. So we have to first find out the weight of the dry soil sample which is going to fill this mold. Now we are using this soil sample whose dry density we have found out from the Proctor compaction test. Now the dry density of this sample is about 1.7 gram per cc or 17 kilonewton per meter cube. Now we know the dimensions of this are 3.8 centimeter or 38 mm and the height is 76 mm. So the volume of this mold we can find out using these dimensions, and knowing the dry density of this which is equal to 1.7 gram per cc, we will calculate the amount of dry soil which is required in this mold as around 146.5 grams. Now assuming a 20% moisture content, the weight of the water will be is found to be around 29.3 milliliter. So we will measure 146.5 grams of the dry soil and mix around 30 ml of water with the soil sample and make it ready. Now we will measure 146.5 grams of the soil sample. Tire the weight to 0. Pour the soil sample into the pan. So now the weight is around 147 grams. This is the dry weight of the sample. Now we will mix this sample with water. Take around 20% of the weight of the water and pour it into the sample and mix it thoroughly. After mixing the soil properly, now we can fill the soil sample into this mold. before filling the soil sample into the mold, we should grease the inside surface of the mold using an oil so that the sample will not stick to the surface of the mold. After greasing the mold, we will take the soil sample and divide it into 3 parts. Now we will fill this in the mold in 3 equal parts, and each part which we are filling will be compacted so that the sample will get filled into this. Now after finishing the first layer, fill the second layer in the same manner. Compact it in the same way as the first layer. After filling the second layer, now we will fill this with the last layer. After filling the top layer, we will compact it again and level the surface. Now level the top surface. After leveling it, we will eject the sample using a sample ejector. This is the sample ejector which is used to eject the sample from the mold. Now we have been using this for other experiments also for ejecting the sample from the mold. So now we will use this for ejecting the sample from the mold which we have formed now. Now we will place the sample on the ejector and keep the top plate. Now adjust the screws. Fix the top screws also. After fixing the sample, now we will switch on the machine and put the lever in the up position. Now the sample will be ejected from the mold. Now take the sample and we will test the sample in the compression testing machine. Now we will test the soil sample in this unconfined compression tester. Now this consists of a proving ring of capacity 2.5 kilonewton. This proving ring is used to measure the load which is applied on the soil sample. This is the deformation dial gauge which is used to measure the deformation on the soil sample. Now coming to the proving ring, you can see it's divided into 20 big divisions, and each 5 divisions is marked 1, 2, 3, 4, 5, 6 like that. The least count of this proving ring is 0.002. So this small dial inside that will represent one full rotation. So the maximum capacity of this proving ring is 5 mm, which can be measured over here. So before the start of the experiment, set the dial, main dial to 0 and observe the small dial reading. Now this is the small dial reading is at 1. So whatever the subsequent readings are, we have to take from 1. This dial gauge is used for measuring the deformation of the soil sample. This dial gauge is also having a main dial as well as a small dial. The small dial is giving you the number of full rotations. The maximum capacity of this dial gauge is 25 mm, which can be seen from this small gauge. Now this full dial is divided into 100 small divisions, and each division represents 0.01 mm. That means when one full complete rotation is over, you will get 1 mm deformation. Similarly, for each full rotation, you will get 2 mm, 3 mm, like that. Now we will fix the soil sample into this loading frame, and then we will start the test. Now before keeping the soil sample into this compression machine, we will measure the weight of the soil sample. The weight of the soil sample comes to about 151 grams. Now we will place the sample into the compression testing machine. Adjust it in such a way that it comes exactly at the center of the plate. Once we start the machine, the load will be applied on the soil sample and the deformation will start. So simultaneously we have to measure the divisions measured along the proving ring as well as the dial gauge. Also we can measure the time using a stopwatch if required. Now switch on the equipment and apply the load. Once the sample just touches here, we will set this dials to 0. Set the proving ring to 0 as well as the dial gauge to 0. Now we will start the experiment. Observe the readings at the required intervals for both the proving ring, dial gauge, and also if you want you can measure the time for each readings also. Now you can see the dial gauge readings are increasing, both the proving ring as well as the deformation gauge. Now for deformation of 50, 100, 150, you can correspondingly note the readings on the proving ring. Basically write the number of divisions in this. In addition to that, if you are taking the reading when it reaches one full rotation, observe the time as well as the deformation dial gauge reading. When one full rotation is over, you can see that the small needle is also moving by one division, which indicates 1 full mm deformation has happened. Now observe the reading till the deformation becomes constant or it starts decreasing. You can observe the formation of cracks also on the surface of the soil sample. For each reading you can measure the time also. You can see that the sample starts failing, some portion is falling down, cracks are formed. Carefully observe when the needle starts reversing. Now we can observe that the proving ring reading is coming back. So now we can switch off the machine. See, the sample has failed and you can see the failure pattern clearly. That finishes the experiment. Thank you.
At MSR UAS, we spark your imagination unlike any other.